For warm introduction, and today I am going to be discuss on long-lived charge-separated porphyrin sensitizers for dye-sensitized solar cells. So before going into my subject, see, I am advising to all youngsters, if you want to pursue their research careers in optoelectronic materials, I am advising you to go through the natural photosynthesis and electron transport systems in biological systems. If you understand well, then it is easy to design the materials for optoelectronic applications. See, while I started my career in biology, but now I'm entering to the organic synthesis and later enter into the physical chemistry. So, how I turned from the biology to the physical chemistry? So just before going to the real subject, just a couple of minutes I will explain about the natural photosynthesis. Of course, everybody knows natural photosynthesis. So what is natural photosynthesis? A carbon dioxide and water molecule in presence of light giving the chemical products. So it is while equation is very simple, but it is not so easy. It occurs only in the plants where the chlorophyll molecules are there. So if you deeply understand about the natural photosynthesis, let's see that there are a variety of molecules are there in natural photosynthesis. One is the carotenes, so where it absorbs in the ultraviolet light of the absorption spectra, and then magnesium porphyrins absorbs in the visible region. And therefore, if you look into the natural photosynthesis, the entire light of sunlight from UV region to the visible region, it will be converted into the food materials. So, very simply that when first carotenes absorb the light, it transfers the either energy or electrons to the magnesium porphyrins, and magnesium absorbs in the visible region, and then it transfers the electron to the quinone system. So as a result, what will happen? A long-lived charge separation species like porphyrin cation and phenone anions is formed. See, people are trying to understand for the last 100 years, but not completely understand. Forget about the model systems. So if you are able to design any model system having the charge separated species in micro to the milliseconds, then you can solve n number of problems to the optoelectronic materials. So that is the reason you see that in natural photosynthesis, the charge separated species lifetime in milli to the microseconds. So that is the reason it is highly efficient. So if you look into the in terms of quantum yields, that each and every step is quantum yield is unit to one. That is the number of photons absorbed by the any molecules and the number of electrons are giving. But in the reality grounds, it is impossible to generate such kind of materials. Okay. Now coming to the subject, so dye-solar cells, it belongs to that third generation solar cells because these are the organic solar cells, because the materials we can design in the laboratory, and the reason is that in the first and second generations we have to depend on the natural resource, and some of them are materials are toxic, and some of them materials are not available within India. So we have to depend on the imports. To avoid all those things, the third generation solar cells, the research is very much suitable to the India, and applications also very much suitable to the nations like India, and therefore the government is also encouraging n number of projects to different agencies like MNRE, DST, DBT, CSIR, PRNS. They are funding like anything to develop these kind of devices in India. Okay, so why we are looking into the dye-solar cells? It is very simple when compared to the other silicon technologies or thin film technologies. See, for example, if you want to initiate the silicon technology industry in India, we need to have thousands of crores of rupees we have to invest. And whereas if this technology is completely commercialized, you can buy the materials from commercial source, and you can sit it at home and you can fabricate your own device. So that is the advantage here. See, here is very simple. A glass substrate, generally glass is non-conducting. So if you want to convert the glass into the conducting, so we have to put into the FT substrate on the glass substrate. And then After that, what will happen? Nanocrystalline titanium dioxide. So you can ask that why only the titanium dioxide. So today, titanium dioxide is one of the cheap material available in the literature, and moreover, is a plenty of titanium is available within India also, and it is a biodegradable. So there is no, once the device lifetime is over, it is automatically degraded. So that is the advantage. So onto which a colored molecule, a dye molecule is coated, and this is called as a photo anode. And similarly, we need another photocathode also. A photocathode is nothing but FTO glass substrate onto which platinum is coated. See, people are with the commercialized products as on today, platinum people are using, and you can ask that platinum is also one of the precious metal and expensive. Now people are trying to replace the platinum with the carbon paste and very fullerene derivatives kind of material, low cost materials. But still the research is in the laboratory level as on today. So after that, the photocathode and photoanode overlay each other and to leave a small gap between the two substrates, so that in that substrate a liquid electrolyte, generally lithium iodide iodine composite, is the redox couple, and then you see it. This is a simple technology. So you can even as on today 10+2 level or BSc chemistry laboratory, we can fabricate this kind of devices. So after that, what will happen when you shine the light, the sensitizer get excited, and then electron in the excited state injected into the TO2 conduction band, from there to the external load, from external load to the counter electrode. So it will complete a cycle. So if you look into this kind of methodology, and very similar to the natural photosynthesis, where the chlorophyll convert the sunlight into the chemical products, and here sunlight converted into the electrical energy. Okay. As a chemist, or everybody, you can look into the, it doesn't matter whether it is a chemist or a physicist or engineering person. So if almost all branches of science have the has to solve the problems associated with this technology. Okay. So how to characterize it? So whether it is third generation solar cells or first or second generation solar cells, the characterization part is the similar. So first we have to see that IPC means incident photon to the current conversion efficiency. See, all molecules in the solution exhibit one kind of absorption spectra, but in the solid state it is a broad because of aggregation. So the molecules are coming close together, and there is a pi-pi interactions. So that is why it is very broadly. So IPC is nothing but at each and every wavelength of the absorption spectra, how many photons are absorbing and how many electrons are liberating. So which means that any molecule having the very broad absorption, like from UV region to the near IR region, then one can expect a better efficiency. And similarly, a current voltage characteristics. So this technology first invented Professor Gretzel in Switzerland, and where he is very lucky. He is very fortunate. He touched the ruthenium complex, so that is why he reported first about the 7% efficiency, and that is the reason third generation solar cells also existing. And not sometimes, most of the times, apart from our knowledge, we need to have a little bit luck. The reason is that he touched the ruthenium complex, and if you see the periodic table, people attempted almost all metal complexes for this technology, but they failed it. So the conversion efficiency is 1% or below 1%. So that is why. So if you look into the deep photophysics of ruthenium complexes, then the singlet and triplet states of ruthenium complexes contributing the efficiency of the device. So that is the reason. So later, very recently, people find about this phenomena. So he is a very lucky person. So that is why, if you don't have the luck, and sometimes we may not get the good results. So what are the drawbacks? See, first of all, ruthenium is not available in India, so we have to import. And second thing, it is that the natural abundance of ruthenium metal is very, very less. And third thing, it is that in ruthenium, while preparing the ruthenium complexes, so we'll get the different isomers. Only one isomer is active. The other isomers are useless. So that is why if you look into the chemical catalog, the molecule cost is about 1 gram cost about nearly 1.5 to 2 lakhs. So the first task is our duty is, we started this research in around 2010 in our institute. Our first task is that how to reduce the cost of the materials. So we are very fortunate, and at that time Professor Grejel patent has expired, and DSIR is also supported a project with to us, and we successfully demonstrated one industry about this process of ruthenium complex. About 1 gram cost is about 25,000. And if you see the chemical catalog, we have transferred the technology to the industry successfully, and the industry has commercialized. And as on today, you see that the chemical catalog, this material cost about 1 gram cost about 40,000. So I'm very proudly say that across the globe, as on today, the ruthenium complex technology is developed from our institute, and industry has commercialized this technology. Okay, now coming to the point. But MNRE in 2011, they said that even though you have developed a technology and the ruthenium is not available in India, so you have to develop a technology, those materials are available within India. Then what challenges we have to take? Because if you look into the literature, n number of dyes are available, but all dyes are not useful. So before taking for example, the chemistry people particularly, before entering into this technology, so we have to keep certain points in our mind. The first thing it is that the broad absorption, the molecule having the absorption from the UV region to the visible to the near air region, only such kind of molecules we can expect a better efficiency. And efficient charge separation. See, I discussed with you now. The charge separation must be micro to the milliseconds. So if it is nanoseconds or picoseconds, then again those molecules will not be useful. Then the redox potential, the oxidation and reduction potential must be compatible to the TiO2 semiconductor metal oxides, and it should have a good anchoring group. And the molecule did not contain the 20 synthetic steps or 30 synthetic steps. If two molecules are mixed together, and such kind of chemicals only will be useful, because commercialization, I'm talking about the technology, not that this is not the basic research. And the solubility, if new molecules must be soluble in some solvents. So if it is insoluble, again we have to adapt the first generation, second generation photovoltaic devices. So that is expensive. So we have to invest a lot of money for establishing the industry. Okay. Now, based on these points, you can see that in the internet, our institute CSR IICT has touched almost all classes of sensitizers, and we have developed for the last 10 years more than 200 molecules. But today I am going to be focused about the magnesium related chlorophyll molecules and their synthetic derivatives, because I cannot speak hours to explain about what type of molecules we are using. Okay. Now we initiated the research in CSR IICT. First, to see that the chlorophyll molecules, what is its absorption? Its absorption is having in the UV region and a visible region, and in between valley is there. So therefore, it is also not completely useful for the conversion of energy, this kind of molecules. And moreover, see, the problem is that when a chlorophyll molecule extracts from the leaf and exposed to the oxygen, it decomposes immediately. So it will not be useful. And another thing it is that, okay, you can fabricate, you can extract in the under inert atmosphere and fabricate the device under inert atmosphere, and that is also, you see that, and each and every year the tree has the leaves becoming the green to the yellow color, which means that the magnesium, the ring, it is the durability is 1 year only. So we cannot use this kind of molecules. So we have to really design synthetic related these molecules in the laboratory and try to apply. Okay. Now, when we started this research, there is only one example is in literature, that is the tetracarboxy porphyrin with 3.5% efficiency. So, which is very, very low when compared to the 10%. See, our target is that MR-first technology. As on today, MR-first technology is 8 to 10% module efficiency with 20 years durability. So we don't want any fancy 30% or 40%. So if you able to achieve 10% efficiency, yes, then we can think about the commercialization of the technology. So which means that the electron cloud is on above the plane of the porphyrin molecule, and moreover you see that there is the absorption, a simple synthetic zinc porphyrin we have taken, the absorption in the UV region and the visible region. So if you can push the absorption towards the near IR region, then we can think about the efficiency of the device. So we started in early stages. We are very unfortunate about, we spent about 3-4 years and we made certain molecules, but the efficiency is below 1%. So the initial stages we struggled a lot, and initial stages also we got severe bombardments for our funding agencies also, and yes, they are really spent the money about the crores, not even lakhs, and we are our group is at that time is very depressed, and we thought that we don't have very luck. Then we realized that. Then we studied the natural photosynthesis very closely. Then we thought that, so we have to change the design concept of the molecule. So we adopted a donor by acceptor systems, and here you can see that a long alkoxy chain we introduced. See, this is meant for the solubility, and the concept is that a donor molecule absorbs in the UV region and the porphyrin molecule absorbs in the visible region, and here it is the acceptor is nothing but the highly electron withdrawing groups are there. So what will happen if you introduce the highly electron withdrawing in any organic molecule? It pushes the absorption towards the red region. So we thought, yes, this is the kind of approach may give the better efficiency. So again here it is that, so when you inject the electron from porphyrin to the TiO2, so then the whole is moved from the porphyrin to the donor. Then we can expect a long-lived charge-separated species. So generally, so what we have done is that a donor is nothing but a simple triphenylamine or carbazole related molecule, and we introduce the thiophene as in the acceptor group. So this is the concept we designed that. So based on that, so there are the variety of designs are available, and then first we initiated with the A3B type of porphyrins, and you can see here is that these are the donor molecules and these are the acceptor molecules, and this is the porphyrin is the astis. So again, why we introduced the zinc here? So zinc is plenty of metal is available within India. So if you can able to design these kind of molecules, then the total materials are available within India and you can synthesize in the laboratory. And if tomorrow having any environmental concerns are there about these molecules, we can redesign this kind of molecules. Okay, then the absorption is slightly pushed towards the red region, and we got about 40 to 50% of IPCE, and the efficiency is about the 5%. Yes, somewhat better than the previous one, below 1%. And now we have to redesign of these kind of molecules again. So this is also not for academic research kind of thing. This is okay, we can publish it. But technology, because why I'm selling the technology, I am representing for the CSR Institute, and they don't care about the publications or academic research. They always think about the technology and commercialization and ECF kind of words. So then we have slightly changed the design structure, but very unfortunately, again here is also and 3% efficiency only. So I am very fortunate when I published this work. I got interaction at that time. Professor Grijal is visiting in India, so he came to the Delhi, and I personally met him in Delhi at that time. So I showed my results because he is the inventor. He can suggest for some alternative things. Then he said that instead of going here, the alkoxy groups you can introduce here. That is only the suggestion he has given. Then you can see that. So here you see that we introduce the alkoxy groups here. So that is the only the design we have changed it, and then you see that up to the in solution up to 750, 800 nanometers, the absorption is pushed towards that reason. Okay, these are all again is okay. So I'm talking about the technology again. So the IPCE spectra. This is the first incident. So you can see here it is that up 300 nanometers to 900 nanometers. This is the first molecule in the literature, single molecule, not the mixture, single molecule showing such a broad absorption. Now we are very happy that CSR as holding the patents on these molecules, and we scale up these molecules also up to 5 grams, from milligram to the 5 gram scale, and we are in talk with the one industry in Bangalore, and they are ready to commercialize our products. And see that we reached up to the 10.2% efficiency. Yes. The efficiency, we are very happy, and our funding agency is also very happy. Now they advised us to think about it, how to further improve the device efficiency, and if not the total technology, at least you can. They requested me to scale up these materials and then supply to the chemical in catalog. So next, we have slightly changed. Yeah, just. Next, we are slightly changed instead of phenothiazine, we introduced the triphenyl imidazole donor molecule, and you see that again 950 nanometers up to is there. So the design concept is perfect. So how I got the idea this one? Just because I'm a biology student as trained, so all those natural photosynthesis or whatever the electron transport systems, because see, this is only the one area of our research. There we are working on volates, we are working on perovskites, we are working on organic solar cells. Then we reached up to the slightly improve the 10.5% efficiency. Okay, then I will go further. So I will skip all these things. So now we see that why this kind of molecule has given the greater than 10% efficiency. So we have to look into the is there any special case dyes or design, and detailed photophysics has to need to understand. See, if you want, it's not possible to jump from 10% to the 20% unless that is a synthetic aspect. Now, if you want to study the detailed photophysics, now I have to go back my MSc. So here we are very lucky that our molecules are similar to the methylene complexes, and these complexes, these materials we can synthesize in the laboratory. And as on today, we are about 5 gram scale, and if industry required even 100 grams also, we are ready to synthesize this kind of molecules. Okay. I will go directly to, yeah. See, I told you that. See, the charge induction is about the picosecond level, and whereas the charge separator state is 30 nanoseconds or 0.58 microseconds. So what is in natural photosynthesis? It is milli to the micro to the milliseconds. So whereas we got the charge separator species in the microsecond. So that is the reason these molecules are showing the more than 10% efficiency. So now, say as a biologist, I turn to the synthetic organic chemist. Now I turn to the physical chemistry. So we have to see, when you see, Sar also said, just synthesizing one molecule and then publish it and forget about it. So we are not doing such kind. We designed ourselves and we synthesize, because see, this is actually more than 20 synthetic steps involved, and we modified the synthesis and bring down to the 10 synthetic steps with the help of the DST or MNRE funding agencies. And now, see, so you can tell that, you can say that, so how stable these molecules? See, I don't have the data as, we studied all the thermal data and then durability studies of these molecules, and these are highly thermally stable up to 200 degrees, and the device is also stable up to the 2 years. Now the task is that, if you are able to, the MNRE has given the task that the 5% efficiency and 5-year durability. Yes, efficiency we crossed it, and durability as on today is 2 years. So very soon I can say that our group, DSSC, we can commercialize based on our technology. So you can see, as in conclusion, we started with the 0% efficiency and then modified to the 5.4, and then with this kind of technology, more than 10% efficiency we got it, and that is because of charge separated species in microseconds. And thanks to my students, these are the 3 students are involved in my project since beginning, Dr. N.V. Krishna, Dr. J.V.S. Krishna, Dr. P.S. Guntur. And I'm very thanks to my funding agencies, DST, CSR, MNRE, Sunrise. So if you name it any funding agency in India, we are very fortunate we got it from the funding to do the research in our institute. And thank you very much for your kind attention. I'm sorry, many of the data I'm not in a position to share with you because lack of time.
Thank you, Dr. Giribabu Garu, for your valuable speech. The dedication and interest you have for the subject is truly motivating. I would like to ask Session Chair Dr. P.G. Rao Garu to present memento, shawl and certificate.
Any questions, please interact with
Sir, what is the size of your solar DSSC? Size?
Of devices?
Yes, sir.
See, initially we are making the devices 1 square centimeter, and then finally we are going up to the 10 square centimeter. Because we don't have.
And what about reproducibility of that material?
Yeah, we can know.
Or firing?
Yeah, we can reproduce. We can reproduce.
With all the similar properties?
Yes, and we are making 5 gram scale of these materials.
Sir, it is possible to increase the efficiency more than 10%?
See, here it is, as on today, efficiency is not the matter, durability is the matter. See, the other part of the research I did not present it, and recently, see, for example, this is under solar system.
Yes, sir.
And recently we developed another technology under diffusal light, like the CFL lamp, LED lamps,
Yes, yes.
and where we went up to the 35% efficiency.
So, sir, one more question. You are saying ruthenium is exporting from other countries, importing from other countries.
Yeah.
So, from which countries they are exporting?
Majorly from Chile.
Sir?
Chile, Latin American country.
Thank you.
Sir, why copper and nickel are not supporting the same theory?
No, see, I explained about, see, in copper and nickel, only singlet state is contributing to the efficiency, and whereas ruthenium, both singlet and triplet states are contributing.
Maybe because of the completely filled state of zinc?
No, not that one, not that one. Copper is not a completely filled.
No, zinc is not.
Zinc is a completely filled. Zinc may not be useful here.